Okay, you guys, so I wanted to step you through some of the basics of mechanical equilibrium here in forces, since you guys missed lectures, or just for those of you that just wanted to rehash a little bit. First off, thing we want to talk about of force in general is anything that's just a push or a pull on an object. So it's a push or a pull, meaning that we're going to take a box and we can push it in this direction, or maybe instead our person decides to pull it in that direction. It's anything that's trying to generate motion of an object, basically, is what a force is attempting to do. So we have push or a pull is a force. Now, units for force. Well, the unit for force is what's called a Newton. Okay, and we're going to abbreviate it because it's named after a person with a capital N, since it's named after Sir Isaac Newton, of course. Now, 1 Newton of force, just so you guys know, is the amount of force required to accelerate a 1 kilogram object at 1 meter per second squared. So that's our unit. Okay, it's kind of hard to tangibilize exactly, but if you think about it, you have a 1 kilogram object, you accelerate at 1 meter per second squared. Well, that's the equivalent of 1 Newton of force. Okay. Now, the major concepts when we deal with forces, we're going to deal with lots of different forces acting on an object. So let's start with a couple of those types of forces. Actually, we're going to skip down here to the vector section. So vector, just like with velocities, have both direction and magnitude. And with forces, they do have both direction and magnitude. We can push with 10 newtons this way, or if somebody pushes harder, they can push with 20 newtons in that direction. The key there is the length of the vector, so how long it is from here to here, indicates the magnitude of the force, or how much force there is. Obviously, the arrow that's on the vector is going to tell you, well, which direction the force is going. That's key for a lot of things that we're going to do. Scalar quantities down here, don't worry about it too much, but scalar quantities just have magnitude. They don't have a direction. So an example of a scalar quantity would be from previously in the semester, like distance or speed. They don't care about the direction of the object, but they do have an amount that they're going to be moving. Other vector quantities are velocity and acceleration are both vector quantities because they can have both magnitude and direction for the motion of the object. Okay, now talking about some of the other principles in here, let's talk about, now we know what a force is and how we're going to represent it. Let's get rid of some of this stuff. And we'll talk about the concept of weight. So weight is the force due to gravity. So when gravity pulls down on you, it exerts a force because it's trying to put you in motion. It's trying to accelerate you down towards the surface of the earth, the core of the earth. Okay, so when you measure your weight on a scale, you're actually measuring how much force you're exerting on the scale due to gravity pulling you down. That's why we call it measuring your weight, because we're not measuring your mass, we're measuring how much force gravity is exerting on your mass trying to pull you down. It's a very simple equation to find the weight of an object. The weight of the object is just going to be W equals mg. So you can see here that the mass and gravity are both going to affect your weight. So your weight will change if the acceleration due to gravity changes. Your mass can only change, well, if you lose matter. So you'd actually have to lose some of the stuff that you have inside you in order to change your mass. Now, one of the other types of forces is called the tension force. The tension force is a force that resists motion. So this is a resistance to motion. Okay. A good example of this, we'll do this over here, would be, let's say we've got a crate, and we're holding that crate, we're hanging that crate from the ceiling. Okay, so gravity is exerting a force downwards, say of 100 newtons on that crate. What the rope has to do is exert a tension force back to hold that object up in the air. The rope doesn't really want to move. So to keep the crate from moving, the rope is going to have to exert the exact same force in the opposite direction, or 100 newtons. Okay. By doing that, you end up creating no motion. There is no motion of the object. And moving on to our next topic, we have a net force of 0 newtons in that case. The net force, basically what that is the sum of all forces acting on the object. The net force is going to determine which way the object moves, if it moves at all. So for instance, if we have 2 people up here, let's draw one person pushing on a box, we have another person trying to push on that box as well. Sorry about how long their arms are. Let's say the person on the left pushes to the right with 20 newtons of force. The person on the right pushes the box to the left with only 15 newtons worth of force. Well, since the person on the right isn't pushing as hard, the box is going to start to move to the left. And it's going to move to the left as if a single force of only 5 newtons was acting on it. So the net force, again, is the sum of everything acting on the object. Now, what's going to happen from here is we're going to end up with specific cases where the sum of all forces is equal to 0. So if we take a look down here, this is what's called mechanical equilibrium. So this sigma right here, what that means is just the sum of all forces. When the sum of all forces is 0 newtons, objects don't change their motion. They don't change from what they've been doing. There is no net force on the object. Okay? So for the crate over here, for instance, this is in equilibrium because it has a 100 Newton force acting down on it due to gravity, the weights, and there's a 100 Newton force acting up, the tension of the rope. Okay? If we talk about another force, we'll show, let's pretend that we've got just a box. We'll go back to our box, but instead it's sitting on the ground. Okay, we have the weight acting downwards, whatever it's going to be. We don't know. It might say it's 100 newtons. Well, we need to have the exact same amount of force moving upwards, otherwise this box is going to fall through the earth. So we need another force going this way, also of 100 newtons. Well, that force right there that's provided by a surface is this one right here, the support force. So the support force opposes gravity, opposes the weight of the object, and supports that object. Another name for the support force is what's called, it's also called the normal force. Now, one key with the normal force is that in this case that I drew before, it's pretty easy. We have the object just sitting on the ground, so the support force is going to totally account for the weight. However, sometimes objects are going to be on ramps or things that aren't perfectly horizontal. In that case, the normal force acts perpendicular to the surface. So it acts at a 90-degree angle to the surface. When we get to the next page, we'll discuss how that looks. So to give you an example of what I mean by the support force or normal force acting perpendicular to the surface, let's flip the page. We will flip the page over. And then on slide 2, we'll see what this kind of looks like. So first example, blocking on a table. So here we have a block, here's our table. Okay, we have our weight going down. Well, we're going to have our normal force going perpendicular to the surface of the table, completely canceling out the weight. The other one, which we don't have to worry about numerically yet, we will get to it later, is if I put something on an incline. So now if I put a block on here, the weight is still going to act downwards, but the normal force is going to act perpendicular to this surface. So here's the plane of our surface. So the normal force will act perpendicular to that. We'll talk more later about the value of magnitude of that force and how it relates to the weight, exactly how much there is, how big it is compared to the weight. But for right now, just understand that that normal force acts perpendicular to the surface. So what we end up with all this net force and everything like that are these two concepts of equilibrium. So we have static equilibrium and dynamic equilibrium. Static equilibrium is the object occurs when the object is stationary. Okay. When an object is stationary, that means that it's not moving, it's not changing its motion at all. The object is in equilibrium, and it's very specifically called static equilibrium. A good example of this is pretty much anything that's just sitting around doing nothing. So, for instance, our block on a table, it's in static equilibrium. The only forces acting on it are the weight and the normal force. And since they're going to balance each other out, there is no net force acting on the object. Dynamic equilibrium is a little bit different. Again, the sum of all forces, okay, or F net, is 0 newtons, but instead of the object being stationary, here the object is in motion. Now, that's great and all, but what type of motion is the object in? So we said earlier that the net force changes the motion of the object. So if the object is in equilibrium with no net force, that means that the motion is constant. And two parts to our motion, that means speed and direction are both the same. An example of this would be an airplane or a car moving at a constant speed. So let's do a car. So we have our car here. It's going to be a box on wheels. There it is on the road. We have the weight canceled out by the normal force. And we have a force pushing the car forward, which is going to be the applied force from the tires pushing on the ground. And then we're going to have a resistance force, meaning friction between the ground and the tires, causing it to slow down, air resistance, things like that. Well, what you'll see is this force here, 1 and 2, cancel each other out. This force here, these forces going up and down, cancel each other out. They're both the same magnitude but opposite directions. So F net is 0 newtons, but the car is still in motion. Now, it took a net force to get it moving, but to keep it moving at that constant speed and constant direction, there is no net force on the car. So, how do we determine net force if things aren't as easy? So, this is where we're going to get into vectors and adding and subtracting vectors from each other. But before we get there, we've got this next slide with little Nellie Newton. So Nellie Newton tells us down here, has a weight of 300 newtons. That's the downward force due to gravity. So we just want to keep her in static equilibrium. So if she's got a force of 300 newtons down, well, that means there needs to be a total of 300 newtons worth of force going upwards. So each of these little guys here is what's called a spring scale. Basically, it just measures the amount of force acting on that the spring scale has to exert to do its job wherever it is in the system. So if she has a weight of 300 newtons pulling down, well, this one spring scale has to pull up on her with 300 newtons of force to balance everything out. In this case, we have 300 newtons down still, meaning, and now we have two spring scales applying a force to Nellie, so each spring scale only has to do half the amount of force. It has to apply 150 newtons. And then we split up into thirds. As she flips herself upside down, each spring scale only does 100 newtons worth of force. In this next one, here, I'm going to give you the answer first. Both of them are actually going to read 300. Okay? And let's talk about it for a second. So we look at this first spring scale, look at what it's actually supporting. Well, this is what's attached to the first spring scale. It's Nellie. So this spring scale has to hold up 300 newtons worth of force to hold Nellie in the air. Now if we take a look at the second spring scale, this one up here, what's attached to it? Well, look at that. It's just Nellie still. And it's a spring scale, which we're going to say has negligible weight, basically zero weight. So this spring scale, just like the other one, is supporting Nellie. So because of that, each spring scale has to apply 300 newtons worth of force. Okay? I could put 5 spring scales in there, it doesn't matter. Each one's still going to read 300 newtons of tension on that spring scale. Here, she's split her weights by holding onto the cliff. So again, we're down to 150 newtons. And here, this spring scale still has to apply 300 newtons worth of force because, well, she's pulling down on it with 300 newtons worth of force. That's how much needs to be applied to hold her up. Okay, now move on. We've got Burl the painter. He stands in the exact middle of his staging. Left scale reads 600 newtons. If he's right in the middle, if this scale is going to do 600 newtons worth of force, then this scale is also going to have to do 600 newtons worth of force to support Burl in his stage. And over here, that tells me that the total weight of Burl in his stage is 1200 newtons. Okay, and the next one, Burl falls a little bit to the right-hand side, so the left scale only reads 400. Since the total weight is still 1200, well, that means that 1200 newtons total needs to be supported, and 800 newtons worth of force is applied to the right spring scale. In the third drawing, now we have no weight over on the left-hand side, which means the right-hand side is you doing accounting for all of the force holding up Burl in his stage, or 1200 newtons. Here we have Manuel's 1000 newtons, board weighs 200, total downward force is 1200 newtons. That means that if he's right in the middle, each spring scale or each scale will measure 600 newtons. When he slides to the left, well, 850 on one side means 350 total on the right-hand side. Now here we have a truck. This truck is 12 tons, the bridge is 20 tons, gives me a total downward force of 32 tons. If 13 is on one side, that means 19 is going to be supported on the other side. Okay, so hopefully that's making sense. All the downward forces have to be canceled out by an upward support force to maintain static equilibrium. Okay. Here, they told us the weight of this iron block is 500. The weight of the crate is 1,000. Well, immediately I know the crate's not falling through the floor, so I know the normal force needs to be 1,000 newtons. Since this iron block isn't moving anywhere, it says it's at rest, that means that the tension on our string has to be 500 to cancel out the iron, keep the iron block from falling. Well, where's that tension force being applied, or where's it coming from? Well, it's coming from this intersection point right here. So those 500 newtons are also trying to pull the block to the right. Since the block doesn't go anywhere, that means that all the forces have to cancel each other out. So the frictional force, again, is 500 newtons. This cancels all forces acting on both of the two objects in our system, allowing for the net force to be 0. Okay, so next worksheet. I'm going to skip that. This one right here. Okay, so now we want to find the net force when things might be acting in different directions than a couple things that we've seen so far. So first one's really easy. If we push 4 newtons up and 4 newtons down, well, that tells me, of course, those two forces are going to cancel out. F net is going to be 0 newtons. Here, in this case, we have 3 newtons to the left, 4 to the right. So that means the net force is only going to be 1 newton to the right. Now, here's where it gets a little bit trickier. We have 3 to the right and 4 straight up. Well, if something were to push, if two people were to push on this block with these forces, one person pushing to the right, one person pushing up, hopefully you guys would realize that the block would probably travel off in that direction somewhere. It doesn't really matter where right now. But we want to figure out exactly how could we take these two forces and turn it into one that would generate the exact same type of motion. Well, it's very similar to what we did with velocities. We're going to take one vector and draw it in from the end of the other one and do the same with the 4 Newton vector. And where those two intersect is going to tell me the net force, or what's called the resultant vector. So this is F net. So if we see here, we have a triangle with one side of 3, the other side of 4, and we want to find the hypotenuse. So we have 3 squared plus 4 squared equals our F net, or C squared, the thing we're trying to find. 3 squared plus 4 squared is 25 equals C squared, so C equals 5 newtons. So the force, if we were to replace, if we were to push with 3 newtons to the right and 4 newtons straight up, it would be the exact same as pushing with 5 newtons of force along the angle that direction that we found. For this one here, it's going to be basically the exact same. Again, pushing down and to the left. Since we have 3 and 4 on the two sides, we end up with 5 newtons again. In the next one, now we have 3 forces acting on the object. To simplify these, the best way to do it is get it down to 2 vectors on the x and y axis. So the easiest thing to do first is take the 2 and the 5 vector and turn that into a 3 Newton vector going to the right. Okay, 5 and 2 are going to cancel out. Thing is, we're still left with that 4 Newton vector going straight up. And, lo and behold, this looks very similar to the first one of these problems. So the length of that net force, or that net vector, is 5 newtons. So that's an easy way to do some of these earlier ones. Next, we're going to go down here to the bottom corner. We're going to do the bottom left and the bottom right one. So there's 2 different ways to do the bottom left. The first is we could do like we did up above. We could do 7 and 7. We do this. And we do 7 squared plus 7 squared. That's 98, which is pretty much 100. So C squared equals 98. C is basically 10. Okay. Now, key here is this 45-degree angle is the key. This shape right here, one side 7, the other side 7, this side 7, this side 7, that makes it a square. That means that this angle right here is also at 45 degrees. Since this 10 Newton vector here and this 10 Newton vector here are at 45 degree angles but opposite to one another, then the net force in this case is going to add up to 0 newtons. This object is going to be in equilibrium. However, there's another way we can do it, which is going to apply to more situations than the way we just did. That way it really only works because of the fact that this is a 45-degree angle. So what we want to do, and because these two sides are equal to one another, the 7 and the 7 are equal, and we created that square. So instead of doing that way, turn the 7 and 7 into 10, let's take the 10 and make it its two component parts. So the easiest way to deal with vectors is that everything is on the x and y axis. So when we have these things at 45-degree angles, we can actually, just like we did with velocity before, turn it into something going horizontal, and then go parallel, hit the y-axis, and turn it into something vertical. Okay, these are the component vectors for this force on the x and y axis. They're going to make it easier to solve because, well, our other two forces are on the x and y axis, and then we can simplify from there. So now, instead of having the two sides, we have the diagonal. So we have our c squared, so we have our 10 squared. Since this is a 45-degree angle, this shape right here, this parallelogram, is this right here, is a square. The diagonal of a square is the only parallelogram that's going to have a diagonal of 45 degrees. So, to figure out the two sides of a square, well, we know Pythagorean theorem is a squared plus b squared, but since a and b are the same, well, 2a squared equals 10 squared. When we solve that, we see that a is approximately, we do 100 divided by 2 is 50. Take the square root of that. Well, it's basically 7 newtons. Well, what does that mean? Well, that means that each of these two forces, going left and going right, are both 7 newtons, or going left and going down are both 7 newtons. So now this 10 newton force isn't there anymore. It's been replaced with 7 down and 7 to the left, and now we can see that the upward force is canceled out by the downward force. The force to the right is canceled out by the force to the left, so we end up with that same net force we found the other way of 0 newtons. Do the same thing with the last one. We're going to take this 10 newton force and turn it into its two components, one going vertical and the other going horizontal. Again, 45-degree angle. Just like before, each of those two vectors will be 7 newtons. And now we can see horizontally, the two forces cancel each other out, so the net force on this object is just 7 newtons straight down. So it can get a little bit more complicated than this, but these are good examples of how to add multiple vectors together to end up with the net force that's acting on an object. The last thing that it's important that we cover is tension forces when things are not perfectly perpendicular, when something's hanging up in the air. The reason being is because we're going to see here how tension can vary based on where the object is that's being held up. First one's pretty obvious. We have our tension, our weight, object's perfectly straight, tension goes straight up. The second example here, we can see that the two strings are actually coming in, so I'll put it on our wall here, the two strings are actually coming in at an angle. Okay? So because we have the weight going straight down, we need a force going straight up. The problem is there's no string left, there's no string there to actually generate that tension. Okay? Since there's no string there, the tension actually has to follow the two strings, going up and to the right and also up and to the left. And you can see here they actually drew in the lines that illustrate that. So to figure out the tension for each rope, for each string, you go from the peak of the vector that you're looking for, the thing you would actually need to hold this object up in the air, which is the opposite of the weight. Okay? And we're going to draw these lines that they drew in, which are parallel to the two strings. Okay, so this line right here is parallel to this string right here, and this line right here is parallel to the string on this side. Okay. Where those 2 points intersect, you can see that they drew in the two force vectors for us. So let me do a quick sketch over here to kind of illustrate this a little more. So we have our weight going down. We need a force going straight up to counteract that. Oh, that's not centered very well. Let's try that again. So we have our weight going down. We need an upward force going straight up, but there's no string to supply that force. So instead, we have to draw in our lines parallel to each axis, and where they intersect the string is where we will see the amount of tension in each of the two strings. Now, what happens here is these two strings aren't just holding the object up. This force right here, we zoom in on it a little bit, actually is doing two things. One, it's pulling our object to the right. The other is it's helping to provide the support for the weight that's being pulled down by gravity. The other side is pulling to the left and also supporting the weight. Because of that, the tension in each of these two vectors right here is going to be greater in sum. The magnitude is going to be greater than the weight of the object. The reason being, they're not just supporting the weight. They're also trying to pull the weight to the left and to the right. So, if we look down here, with A and B, we draw our parallel lines in, and now we actually see that A is longer than B. Well, why is that? Well, A is actually supporting more of the weight than B is. If we were to draw our vertical lines over, we would see that A is supporting that much of the weight. B is only supporting until that point right there. They're both, again, pulling to the left and to the right with the same amount of force, canceling each other out, but the tension in A is much stronger than the tension in B because it's holding more of the weight. If we look down here, the one that's a good example is one where everything's spread really far apart. We need a force going up that way. We don't have it. So when we draw in our parallel lines, we can see the tension is drastically increased when we stretch this object out. Well, why is that? Well, the reason that is because so much of the force for each of these two is pulling sideways instead of just supporting the weight. Because of that, you see a massive increase in the amount of tension because we're pulling to the left and to the right. So hopefully this clears up some of the questions for you. I'm going to send you a couple other worksheets that go along with it to practice. There is a quiz that goes along with equilibrium, forces, and tension and that kind of thing. Not much in terms of calculations except for finding net forces with multiple vectors. So other than that, hopefully it's cleared up some of your questions, and we'll see you guys later.